Thank you, and thanks for having me. It's good to be here. So I'm going to talk a little bit about some work in forensic science, and in particular in digital forensic science. And the work I'm going to talk about is that of Sophie Nightingale, who was up until about a couple of weeks ago was a postdoc in my lab and just started a faculty position at the University of Lancaster in the UK. So let me start with a little bit of background. About 10 years ago now, a little bit more than 10 years ago, the National Academy of Science produced, I would say, a scathing report on the state of forensic science. And one of the key insights in this report was the following. Our key finding was that, with the exception of nuclear DNA analysis, no forensic method has been rigorously shown to have the capacity to consistently and with a high degree of certainty demonstrate a connection between evidence and a specific individual or source. That's a long way to say that with the exception of DNA, forensic identification does not work reliably enough to be used in the courts of law. This was in 2009. Just recently, one of the authors of this report wrote, 10 years on, we are still struggling with the inability of the courts to test the efficacy of forensic evidence. And so there has not been a significant improvement in the use of forensic identification beyond DNA fingerprinting. And we have been particularly interested recently in the use of digital techniques. I'm not going to talk about fire pattern and bite analysis and hair and fiber, all of which have some pretty significant problems. I'm going to talk about some digital techniques. And this work was inspired by a very nice article by some folks at ProPublica, which was titled, "The FBI says that its photo analysis is scientific evidence, scientists disagree." And this was a fairly critical article of how the FBI photographic forensic evidence group uses information from photographs to try to identify individuals in crime. And what that article pointed to was several pieces of photographic forensic identification. I'm going to talk about just one of them, which is this blue gene analysis. So this is a figure from a paper by Richard Vorderbrugge, who is then and now an FBI photographic analyst at Quantico. And what Richard was arguing was that you can use the pattern of wear and tear along the seams of your jeans. So if you're wearing jeans, I am right now, and if you look at the inner seam and the outer seam, you will notice that where that stitching is, there is a pattern of wear and tear that of course just comes from washing over and over again. That pattern is not perfectly smooth, so things that are elevated wear more than things that are lower. And it was argued in this paper and has been used in evidence in courts of law that by matching that pattern of wear and tear, as Richard calls them, valleys and hills, you can identify somebody from a photo in, for example, a bank robbery, which is where this was from, for example, a pair of jeans that was taken from a suspect's closet. Now, in this paper, which was published, and in this technique that has been used in the courts to identify individuals, Richard wrote in many places something that sounds a lot like this. A determination of whether individual characteristics, like the ones discussed herein, the pattern of wear and tear, are unique or not, will remain unanswered until validation studies can be conducted. Until that time, the ability to individualize an item based on a single such characteristic will remain a matter of opinion. So what Richard did in this paper from, let's see, I think it was 1999, was say, look, here's an idea. Maybe we can identify people, but he didn't actually validate it. He didn't look at a large scale study. He didn't ask what the detection rate is. He didn't ask what the detection accuracy is. And despite that, this technique has and continues to be used in courts of law to match people. And this is just one example of clothing-based identification. I'll talk about a few more at the end. So Sophie and I wanted to sort of set out and try to understand whether this is a reliable technique or not. And so here's what we did. I'm going to tell you a little bit about the study. So the first thing we need is we need lots and lots of different pairs of blue jeans. So I only have 2 pairs in my closet. Sophie had 4 pairs. That's obviously not enough. So here's what we did. We went on to Mechanical Turk, crowdsourcing site, and we asked people to take a pair of blue jeans out of their closet, to print a ruler that we provided to them as a PDF, and to take 4 photographs with each leg and then the outer seam and the inner seam laid on top of this. And we gave them directions on well lit, hard surface, camera above. And so that we could see the pattern of wear and tear. And of course, we have a ruler so we can actually measure this in real world units. So we gathered a total of 111 pairs from users across the country. This is Sophie right here. She spent several days going to all of the secondhand shops around UC Berkeley and buying blue jeans. People thought she was really weird because she was literally buying hundreds of pairs of blue jeans. By the way, we donated them all back to the secondhand shops after we were done with the study. So we also collected 100 pair of jeans and photographed them in the same way that we asked Mechanical Turk users. So now we have 200 and change distinct pair of blue jeans, 4 photographs each, inner, outer, left, right. And what we're going to ask is, how distinct is this pattern of wear and tear that purportedly can be used to identify an individual? Okay, so let me talk a little bit about the underlying analysis, and then we'll talk a little bit about the accuracy of this technique. So each image looks something like this. We have the ruler here. So the first thing we have to do is calibrate everything to real world units. So we wrote a little interface where the user can specify 30 centimeters on the ruler from beginning to end. And then we pick a 30 centimeter chunk along the seam. We start where the bottom cuff meets the vertical seam, and we extend a vertical line to be exactly 30 centimeters. So we extract a 30 centimeter chunk. We rotate that image and we grab the seam. So now what you're seeing is that pattern of wear and tear, dark light, dark light, dark light. Yep. Now, one of the things you'll notice here is that that seam is not perfectly straight. Of course, it's fabric. So what we do is we manually, so this is the second manual step, pick 10 points along the seam, and we fit a B-spline or a bicubic spline to this to get what is that sort of curviness of the seam. So once we have that, we then grab a, let's see, what is that? Yeah, 30 pixel region of that pattern of wear and tear that you see there. And the reason we're going to do this is we want to integrate out any little bit of noise that comes just from the underlying texture. So we have 2 splines now that are offset by 30 pixels. This part is automatic and actually relatively easy to do. And then what we do is we integrate along the orientation of the spline, and we get a 1D signal. Okay, that 1D signal is shown in blue. You can see it's very noisy because of the underlying pattern. We low pass filter that with a standard low pass filter to get the red curve. And then we convert, and you can see, by the way, that this valley here corresponds to that dark region there. This hilltop here corresponds to that bright point right there. So you can see that pattern of up, down, which is the dark light, dark light. And then we take that and we convert it into a binary signal where you either have a +1 value corresponding to a bright value, or a -1 value corresponding to a dark value, or 0 where you're in the transition. So these are just the 0 crossings here. So the full pipeline, there are 2 manual steps. The user has to determine the ruler, the pixel to centimeter conversion. The user has to specify 10 points along the seam, and then everything after that is fully automatic. I should say that in the original FBI paper, the entire process was done manually. The analyst would pick which dark and bright spots to analyze manually. That obviously is incredibly subjective and dangerous in a forensic setting. So we sought out to automate as much of that as possible. So with the exception of specifying the seam, everything is now automated. So now this is the signal. This is the signal that we want to ask, how distinct is it for different pairs of jeans? All right, so here's how we're going to do that. We're going to take 2 pairs of jeans, these are 2 different ones, and we are going to run that same analysis that I described to you to get a 1D signal. And now we want to ask, well, how similar is that seam to that seam? Okay, and we're going to do different lengths depending on how much of the leg that you can see. So we don't know exactly where to start the seam. You know, we have this sort of rough starting point over here where the bottom cuff meets the vertical line. So there's a little bit of slop in there. So what we do is we grab a chunk from one of the pants, and then we grab the same chunk from the other pants, but we wiggle it by plus or minus 16 pixels and find the maximal alignment between the two. I'm going to show you in a minute how we do that measure of alignment. So we allow for a little bit of misalignment. And then we slide this window over a little bit more, and we do the same thing, and we do it again, along the entire 30 centimeters. So this is, and what we're going to look for is what is the maximal match between these two as we move the sliding window along. And I'm going to show you different lengths of that sliding window as we move along. All right, so now the question is, well, how do you compare two things? So I've got the two seams, I can extract this 1D signal, I'm going to match them by looking for windows that match, essentially a cross correlation type thing. And now how do you assess whether two of these signals are the same or not? So they're clearly not Gaussian, so I can't do correlation, that wouldn't make any sense. So what we're going to do is we're going to leverage some techniques from the neuroscience literature that has metrics of similarity of spike trains. These are basically spike trains, so these look a lot like a neural spike train. And I'm not going to go into the details of this. It's in the paper that I'll give you a reference to at the end, and it's in this paper too. But the basic idea is that you measure the similarity of these using two basic ideas. One is, how many spikes do I have to add or remove to make these two spike trains the same? And how much do I have to wiggle an existing spike to align with a spike here? So for example, if these two spikes are very close, well, a little bit of wiggle here will match here. If there's an entirely a spike missing, I have to add a spike. So a combination of those two ideas, how many spikes are missing between or added between the two, and then how much do I have to wiggle them, is our measure of similarity. And again, I won't go into the details of how that works, but I think it's a relatively intuitive and certainly better than doing correlation on these very non-Gaussian signals. All right, so that's the pipeline. Right, for comparing with those 200 genes. We now have a pipeline, we can process them. And now we're going to talk about the similarity for each of the inner, outer, and we're going to integrate over left and right because there's no difference between them. So what I'm going to show you here is the length of the seam that we are going to compare is 24 centimeters out of a total of possible 30. So that's where we move that 24 centimeter window from the bottom to the top in chunks of 16 pixels, looking for the maximal match, right? Find the place where these two things match the same across all pairs of the 200 plus genes. So I compare gene 1 to 199, gene 2 to 198, and so on and so forth. This is the distribution of the similarity that I just mentioned earlier. So a low similarity, this is not a great word now that I see it. So a zero similarity means these are exactly the same. And as the number gets bigger, it's more and more dissimilar. So this is really a measure of dissimilarity. The way to interpret these numbers is 15 means that you have to add 15 spikes on average to get two signals to match. And you have to move the spikes by, on average, 15 pixels to get them to match. That's that intuition for that number right there. Okay? So this is the similarity or dissimilarity between distinct pairs of genes where the seam is of length 24 for the inner seam. Good. So this is if the seam is 18 centimeters and 12 centimeters. So why would I care about this? Well, I don't know how big of a seam I'll be able to look at. I may be only be able to see part of the gene. And you can see something very intuitive, that as the seam that you're comparing gets smaller and smaller from 24 to half that, well, they get more similar. That is, I can find a region on these two things that actually look pretty similar because it's a relatively small chunk. And obviously, if we kept going, the likelihood of a match gets higher and higher. But the bigger the seam, the less likely it is to have a false match. Okay, so that's for the inner seam. So that's in the inside of your legs. And for the outer seam, you see something fairly similar, but they're a little bit more similar. I'm going to show you the numeric values in a second so you can see what these are. And if you look at your genes, you will notice that the seams on the inside and the outside of the genes tend to be a little bit different on how the fabric matches, and that's probably what we're seeing here. So just to give you some numeric values, so remember on the previous slides, I told you I integrated over the left and the right because there was no difference. So this is the measure, this is the mean measure of similarity for seams of length 24, 16, 12, and 8. I didn't show you 8 on the previous one. For the left, the right, and then the combined left and right. So for 24, the mean similarity is 14. Again, the way to interpret that is I have to add 14 peaks and troughs, and I have to move them by 14 pixels. And as the seam length that I'm analyzing reduces, my similarity reduces proportionally. That's completely intuitive, and that's what you expect. What's in square brackets here, by the way, of course, is the standard deviation. So that's for the inner seam. And here I'm going to just show you, this is the minimum error. That's the best possible match between two. And this is the median error. And you can see the reason I'm reporting this is it's not just that it happens to be that there's two genes that are really, really similar. You can see that the difference between the min and the medium is not that big. So there's actually a lot of similarity across these genes. It's not like the median is 50 and I just happen to find this one that is very, very similar. You can see even on average, it's actually, not that dissimilar. Okay, so that's the inner seam. This is the outer seam. You can see the values here are just ever so slightly smaller than for the inner seam, but roughly about the same. Okay, the same pattern exists both for inner and for outer. All right, now the question is well, what does that mean? What does a similarity or a dissimilarity of 14 mean? Well, it only means something if we ask, well, if I have the same pair of genes and I make the same measurement, how similar are they? So that's the question we want to ask. Now I've done the comparison across distinct pairs, and now we're going to do the comparison within pairs. So what we did is we took a whole bunch of genes of ours that we had, and we re-photographed them over and over and over again. So this is one pair of genes photographed 4 times, the left inner, the left outer, the right inner, and the right outer. And we did that 10 times each for 10 pairs of genes. And you can see here what we did is we basically took the pair of genes, we spread them out, we made the measurement. We picked them up, we spread them out again, maybe on the same surface, maybe on a different surface. We used the same camera, maybe a different camera. Similar lighting, different lighting. And we just wanted to see what is the reproducibility of making this measurement. And then we're going to look at the similarity for within the same pair of genes, identifying somebody, and then across, and then we'll get a sense of whether this is a reliable forensic identification technique or not. Exact same pipeline that I just described to you for the distinct pairs. Again, pixel-based similarity. 10 means you move within 10 pixels. You have to add or subtract 10 spikes. This, of course, is the histogram count for the inner and the outer, just for the 24 length, the longest length, which is the most distinct. Okay. So here you can see things are shifted downward a little bit. You can see it's a little bimodal. I won't talk exactly why that is, but in the paper we explain where that bimodality comes from. So is that good or not? Well, let's compare it to the distinct pair of genes. By the way, I should have mentioned that the red curve here is a Gaussian fit. It's a normal distribution fit to the underlying data. It's very, very normal distributed. So this is same pair of genes. These are different pair of genes. Same, different, inner, outer for the length 24. And so first of all, you can see quite a bit of overlap. So what would you want? Of course, you want these distributions to be shoved all the way to the left. They have 0 dissimilarity. And you want these down here to be all the way to the right, and then you can draw a clear line in the middle. That's obviously not happening. So now we can measure the detection accuracy and the false alarm rate. So what I'm plotting for you here on the horizontal axis in log units is the false positive rate. So this is so 1 times 10 to the minus 1 means 1 in 10 false positive rate. 10 to the minus 2 means 1 in 100 false positive rate, up to 1 million, 10 million, 100 million. And on the vertical axis is the true positive rate. So obviously, if I have a false positive rate of 100, I have perfect classification. Good. Now, I have a 1 in 10 false positive rate. My detection accuracy, I should mention that the blue is for the inner seam, the red is for the outer seam. So notice how quickly, just down to 1 in 10, my detection accuracy goes down to about 60%. Let's do the 1 in 1,000. So 1 in 1,000 is 10 to the minus 3. My detection accuracy is about 40%. And now you can see things we're in a lot of trouble, because what do you want a forensic technique to be? Yeah, 1 in the millions or so. So that's 10 to the minus 6. That means detection accuracy with 1 in a million is only about 20% of the time. So only 20% of the time can you accurately identify the same pair of genes in this very, very controlled setting, which we'll talk about in a little bit, with even a reasonable false alarm rate of 1 in a million. So these genes are just not that distinct. Now, it's not just numeric. It's not, I mean, I'm pushing around numbers. So here are the 2 genes that we found. Both of them were from mechanical, well, and both of these are that we purchased from the secondhand shops here, 2 different pair of genes. And this is one of the 24 centimeter length genes from one pair and another pair. Similarity 7.7, highly similar. And you can see they actually look pretty similar. There's actually a fairly common pattern among them. A little bit of differences, and this is only across 200 pairs of genes. So if I expanded this to 2,000, surely I'm going to just start to find things that are basically war and tour across even a relatively long 24 centimeters, which, by the way, 30 centimeters is about from your cuff to about your knee, roughly. So it's actually a pretty long segment. These things are just not that distinct, it turns out. Now, we took this continuous signal and we binarized it. And the reason why we did that is because that's what was done in the original paper. All they looked at was the peaks and the troughs of these bright and dark spots. But arguably there's some signal here in the continuous domain. And maybe if we actually use the entire continuous signal, the low pass version, we could do better. So we tried that. It turns out you can't do better. So inner, outer, 24 centimeters, same, different distribution. Here we're going to use correlation now as a measure because those are normally distributed signals. And here you can see exactly the same problem. There's a huge overlap in the distributions for the same and for the different. And in fact, you get almost exactly the same true positive, false positive trade-off, even when you use the continuous signal. Now, that was looking at only a single seam at a time. So maybe I can see 2 seams. So if I'm standing like this with my legs separated, maybe a camera from the side can see my right outer and my left inner leg, and maybe I can combine them. Well, you can combine them if they're statistically independent. So let's find out if they are. So we're going to look at the correlation between the left inner and the right inner seams. How correlated are they? And here you can see that the R values for the left inner and the right inner is 0.4, let's call it. For the left outer and the right outer, it is 0.5. They are not independent, okay? So you can't just blindly combine them. Now, the correlation between the left inner and the left outer is getting closer to independent. That R value is only 0.1, and for the right inner and the right outer, it's 0.1. So this makes sense. The inner seams are stitched in a similar way, the outer seams are stitched in a similar way, and the pattern of wear and tear is not independent. But there is relative independence between an inner and an outer seam. And we can play the same game, left inner, right outer, etc. And those are relatively independent. So if you can see 2 seams, both of length 24, you might be able to get a slightly more distinct pattern. Now, I should say a few things here. So one is, we made these measurements in incredibly careful, controlled lab environments. We had both pair of genes we were comparing were stretched out on a firm surface. They were calibrated. We had a light with no perspective distortion, a camera with no perspective distortion, well illuminated. That is very different than the types of images you see in CCTV that look like this, where the pants are all bunched up, there's perspective distortion, it's noisy, you don't have calibration. And so even in the best controlled settings, these patterns are not very distinct. That is surely a lower bound for the accuracy when you go into the wild and start using these techniques where you have a lot more uncertainty in the measurements that you are going to be making. So even in the best of situations, I think we should be worried. Now, what we're currently working on is expanding this analysis to look at the accuracy and efficacy of other clothing-based forensic techniques. So this is another one that was pointed out in the ProPublica. This, by the way, is Richard Vorderbrugge right here. He is wearing a shirt that was seized from a suspect in that bank robbery and comparing the mismatch of the stripes, the plaid stripes on the back, the front, and the shoulder, and has argued in court that misalignment is distinctive enough to identify an individual. And so we are looking at, right now, in fact, I have a big box right here with about 100 shirts striped plaid shirts, exactly looking at that pattern to see if in fact it is distinct. We're in the early days of this, but I can tell you in the early analysis, it absolutely is not distinct. And this is a real problem because this technique has been used many times in the courts of law. That's work that we're currently working on right now. I have a new student coming in who's also looking at this pattern of clothing. The FBI has also used the pattern of camouflage, how these patterns sort of match, and whether that can identify an individual, whether it is unique. So I have a new student coming in who's going to be looking at this as well. I'll end, and then we hopefully have some time for questions with a couple of quick thoughts. One is this work on the genes was published recently in the Proceedings of the National Academy of Science. This is the citation. Sophie is the first author on this and did all the heavy lift on the work on this. It was, by the way, a huge amount of work to collect the data and to analyze the data to really build these things out. For too long, I think this type of photographic identification being used in the courts, being promoted by the FBI, has not been proven to be reliable. We don't have a bone to pick. If it was reliable, we'd be happy with it. We are happy to use these forensic techniques if they're reliable, but we think that these things need to be validated, and I think they should be validated outside of law enforcement, and who better, frankly, than academics to do this type of work. So we have a whole new research agenda looking at both clothing-based and also other types of photographic identification to understand the uniqueness of these measures, the error rates of them. We've been doing everything in these very careful, closed, controlled lab environments. And the next step is to really take these out into the wild and see how bad does this get when you actually use these techniques in the wild. And I think it's reasonable to think that things are going to get much, much worse, but I think we also need to know that number as well. All right, thanks very much. I think I'll stop here and let David take over, and we can field some questions.
Great, thank you so much. So I'll applaud on behalf of all the audience that they are applauding. The audience, please put your question either into the chat or into the Q&A area. And I think ideally what we would like is for you to ask your question yourself rather than me repeat them. That's what Hany would prefer as well. So we have a comment, clap, 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 clap. So I will start with a question myself, and as the audience, please, if you have a question, place it in either chat or Q&A. So one question I had was about the odds that get quoted for things like this. So yeah. I think the in the one of the cases that used genes, I saw that they quoted something like 1 in 650 billion odds that this would so, that it would match. So
good.
First
did they
of
come
all,
up with that number?
How did they come up with that, which is clearly wrong?
So
and
number,
second of all, is there a good way, like now that you've done your analysis, could you do something that's actually a reasonable one?
Good. So that number was not for the blue jeans, but it was for the plaid shirts. And the reason, the way he came up with this will absolutely shock you. So here's the analysis. So you've got a plaid shirt. Let's just do two patterns, right? You've got the front pattern and the back pattern, and the stripes don't quite match up. So what Richard did is he looked at the misalignment of the first stripe, and he said, what's the probability that those two on the shirt in evidence and the shirt that we see are the same? And he had some sort of hokey measure of pixel error, but okay, fine. And then we said, okay, those align within this distance, and then the next line also aligns. So I'm going to multiply those two probabilities. He seems to have forgotten what statistical independence is, because once you determine that first mismatch, it's all the same. There's no independence. So he multiplied, 1 in 100 by 1 in 100 by 1 in 100, and he came up with 1 in 650 billion. And I think the line was, by the way, plus or minus 5 billion or something like this, which is patently absurd. So there were so many problems with that analysis. The way he came up with the first measure was nonsense. And then with ignoring statistical independence was really bad. I mean, really bad. So now in our case, you'll notice we didn't go beyond. So even with just 200 pairs, we could do the all pairs combination. So that's a reasonably big number. And the reason we fit that normal distribution was that so we could measure false alarms. to relatively low. We didn't feel comfortable going below 1 in 100 million. Because even with that normal distribution, once you're in there, you're really in the tails of the distribution. So we stopped at 1 in 100 million. I think if you want to get into the types of numbers that you see with DNA and the billions, you just need a lot more data. Honestly, it was a huge amount of work just to get 200 pairs of blue genes. So one of the difficulties here is, and so the shirts that I was just referring to earlier, I have hundreds of them. It's costing thousands of dollars. And so it's really, it's tough to get this data. And it's tough to really ensure that the data is representative, right? There's lots of manufacturing out there. There's different plants. Is it manufactured in the US and Mexico and China? What is the quality? So you're really coming up with those hard in the billions number, I don't think you're going to get to. My hope is I can get into the low millions. That would be success for me. So I think we have to be honest about the statistical inference that we can draw.
And is there any way to test it after the fact? So like you come up with some number, can we go through old cases where they came up with these numbers and like see how many were overturned?
Yeah, that's a great question. I don't know. Part of the problem is we only know about the cases that were actually litigated out. We don't know about the cases that settled, which is 95% of cases, right? So I've worked lots of cases where I see forensic reports from law enforcement with lots of fancy numbers in it, but those things never see the light of day. So I think that's the right question to ask, because as I mentioned, we're doing everything in a controlled environment. So how is this really going to map out into the real world? So we do want to do some real world environments where we actually have people wearing the clothing and photograph them. I think that's a good step in that direction, but it's still pretty far removed from the reality of, real forensic identification. And that worries me. So, what I always say is this is the lower bar. We have, so it's only going to get worse from here. And so if you have a 20% detection accuracy with a 1 in a million false alarm rate in perfect situations, I think you have to abandon the forensic technique until you can come up with something better. It's just only going to get worse from there. Now, if we had gotten a 95% detection accuracy with a 1 in 10 million, well, then I think it's really important to do those follow-on studies. But if we can't do very, very well in lab, in controlled setting, I don't really know what we're doing.
Questions from the audience. Here, we do have a question from Jason. Jason, do you want to unmute yourself and ask your question?
Yeah, sure. So my question was, are groups that might not want to be surveilled by these methods that are maybe forensically questionable, are they responding to the fact that these are being used and maybe not wearing plaid shirts, or
yeah, that's great,
or rolling up the cuffs of their jeans or something?
Yeah, that's great. I mean, certainly. I mean, so first of all, let's give the FBI credit. It was a clever idea. I actually thought, like, if you think about it, you're like, sure, there's a very non-deterministic, highly chaotic system of how the gene pattern is sewn and worn, and I think that was a really clever idea. When I first saw it, I'm like, hey, that's pretty cool. But it turns out it actually doesn't work that well. So now to your question, sure, once you know that the FBI is looking at pattern of wear and tear on jeans or plaid shirts or camouflage, sure, wear a black t-shirt and wear black jeans where you can't see the seams. Like, so we couldn't do this on black jeans. It was very, very difficult. It really worked best on blue jeans. So sure, you can imagine countermeasures essentially that would be fairly easy, or paint in some of the seams on your jean, right? Honestly, I think the people who are probably committing bank robberies aren't reading the PNAS papers. So my guess is they're probably not fully aware. And these techniques are not, it's not like DNA. Everybody's familiar with DNA. These are used, a couple dozen times a year, right? And so it's not one of those sort of high profile things where everybody is aware of it. But sure, once people are aware of it, it's pretty easy to figure out how not to do this. And by the way, as we've been seeing a lot of protests, both here and abroad, and a lot of social media photographs and surveillance photographs, people are trying to use distinct clothing to identify people at protests. And so this is not a hypothetical technique that is being used. It is actually being used because a lot of people, well, particularly today, everybody's wearing masks. So face recognition doesn't work anymore. And so I've seen more and more of this unfolding. And so, yeah, I think you're probably right that people are going to start getting smart about this.
I'll ask another question as and audience, you can ask questions in either the chat, and I can read your question if you prefer that. I was wondering if, is there any notion or version of doing forensic science where in this sort of double-blind sense, like in analogy to a medical trial, or like, I guess a police lineup is supposed to be this way, where even the officer does not know who the suspect is.
Yeah.
Is that happening in this kind of forensic science that you talk about? And it is even possible to do it that way?
This has been a criticism. So I can't speak definitively about this across all the forensics lab at the federal and state level. That's very difficult. But I will say, in the ProPublica piece that I mentioned, and in other investigative reporting that I've seen, and in talking with prosecutors and forensic analysts, there is a fairly cozy relationship between prosecutors and federal forensic lab, and that is not good. And it should absolutely be the case that these are blind. That you should not. The prosecutor shouldn't tell you, we think this is our man or woman, and I do think that, if you will, conflict of interest is very serious. There have been problems in the past with this, that cozy relationship. I think these things there has to be a firewall between the forensic techniques and the prosecutors, and there is not, as I understand it now. Again, I can't speak to all the different forensic labs around the country, but I absolutely agree with you. I will tell you, I work a lot of forensic cases, not just this type of identification, but also analyzing images if they're real or not. I have to work really hard to remain sort of neutral in this. The hardest thing for me when I work a case is when I like the lawyers, because there's this innate ability, you want to sort of please, there's this innate instinct to want to please people. And so I like when I work for a lawyer that I really despise, because it makes it really easy to do my job. When I really like them, it's hard. But I do think it's really important, and it's very, very difficult. You don't even know where your biases are when you go into these things. So I think that's something that the forensic community has not actually done very well, frankly, and I think we can do better there. I think there's a question. So I
had another
Jason
question. I'll just ask
Jason.
it.
Yeah.
So you mentioned that some of these forensic techniques are getting really wild claims of accuracy. And that gets put into evidence in courts, and it's like, what is the appropriate accountability to be like?
No, that's the right question. Yeah.
How do you there should be laws about how these things are put in court that make sure that they're appropriate accountability. Like there has to be some external review or something like we have with medicine.
So there are rules for introducing forensic science. There is the Doe-Bear standard, which is becoming the standard around the country now. I'm sure most people know about that. But here's where things get really messy, in my opinion. The courts like precedent. So what happened with these clothing-based identification is early on, that blue jean technique got allowed in a court. And then when they went to use it again, they said, look, that court over there allowed it. And then the judge is like, great, I don't have to worry about this. It was already allowed once. Nobody makes mistakes apparently in the law, so let's not revisit it. And then once the blue jean was in, when Richard went to go do the shirt one, he was able to use the blue jeans as the precedent for that. So that got introduced, right? Now, there are standards for introducing forensic evidence. It has to be in the reproducible. You have to know what the error rates are. It has to be accepted by the community. Those were not the case here. So they made a mistake early on. Okay, fine. But then the court keeps using the precedent, right? Now, what happens is that this can go both ways. If you eventually can get something kicked, Well, then it never gets introduced, because then the defense simply, if they know about it, can say, look, that court did not allow this type of forensic identification, and now we have to. But the problem is the precedence is this sort of steamrolling of these techniques. And I don't think, I do a lot of, not a lot, I do occasionally, I do training for federal judges and for prosecutors, and the level of their science and technological understanding is really, really low. And that's not really a criticism. I mean, they're lawyers, right? But they don't even understand what they don't understand. And we are asking them to assess fairly complex forensic techniques and technologies. I personally don't like the adversarial model that we have here in the US of jurisprudence. I prefer the Western European, which is one of inquisition, where people like me are not hired by the defense or prosecution. We are hired by the judge. The judge says, look, I need a smart person to come talk to me about forensic science. I'm not, this is perfect for me. I don't have any sides. I'm just talking to the judge. And by the way, in this country, judges can do that, but they rarely do it. But a judge is allowed to call their own expert. I actually think this is the way we should do it. Forensic science should be taken out of the adversarial system. Let's talk about it in the most objective way possible. That's what I think we should do.
One comment that you made there, to me suggests something that I think, maybe especially brings computer science and law together, which is that this notion of precedence and sort of how law evolves is something that like a law is evolving and becoming a standard because of one false decision by some judge somewhere, and now all of a sudden everyone's copying those false decisions, and it's like, that's crazy.
It's sort of the exact opposite of science, right? The very nature of what we do is we keep refining our understanding of these things. We don't take something from 20 years and be like, done, right? We don't have to talk about this anymore. So that is something that's fixable, by the way. I will tell you that under former President Obama, there was a task force tasked with looking at that National Academy of Science report that I mentioned at the beginning of the talk, and really trying to sort of get at, where are the problems and how do we fix them? Unfortunately, that task force was completely disbanded when Trump took office. Sessions, his first order was to disband this task force. I'm hoping that under a new President Biden and Harris administration, we can start having this conversation more seriously, because there are real problems across forensic science. That report from 2009 basically could have been written today. With the exception of DNA, it's not pretty. And the number of wrongful convictions, the number of people who plead out that we don't even know about, is astonishing based on some pretty shaky science. And I think that's a fixable problem.